Hi everyone, we're finishing up the first half of chapter 8 and I wanted to make sure that I went over the review with you because the reality is you're going to have to take the test before we go back. There's just no way to get around it. Last I heard, the governor wants us out until April 15th. Um, that could change, who knows, and I want to make sure that you get all the instruction that you need. So, in order to make it as personalized as possible, I'm probably going to have to video chat at some point. We could use Facebook Messenger if you have Facebook. We can use, you know, we're not supposed to use Zoom because of a parental consent of some sort, but Zoom seems to be the most preferred by a lot of people, and I know a lot of people use it across the state. That being said, I don't have a problem using it if you're 18 or above and you make quote-unquote adult decisions. It's just a quick, live chat where I can see where you are in your notes in the curriculum and gauge your understanding of the chapter so far. I'm not testing you, I'm just asking your opinion, kind of to see where you're at. If you would much prefer to send pictures, individual pictures of your notes that are done, that's fine. There's a lot of them. And if you want to just send me a message of your understanding, then I don't need to really talk to you in a video or anything either. But again, I'm going to have to figure all of this out over the next couple days because I want to make sure that we're not lagging behind and that we're all understanding what's going on. That being said, I want to give a nice thorough review for this chapter. There are assessment questions on this test, and what I think I would probably end up doing is hand delivering. Actually, I don't have access to the test. I'm going to have to figure out how to make the copies of the tests, but either way, I plan on hand delivering them. I can put them in your mailbox, I can drop them off at the curb, whatever the case may be, and then I can come around and do that again, grab them, pick them up or whatever. But I know for myself I need hard copies. So obviously you can use your resources, but I ask that you would do this with integrity. No internet resources, don't work with each other. What would be expected in class. So moving forward, 8.1 we skipped over because it was just a review of everything we talked about. Basically figuring out what would be the best option possible with the tools that we already know. At the point of 8.1, we knew U-sub. We knew something with trig identities. We knew sum or difference rules. That just means like if you're taking the integral of a polynomial, you integrate each of them separately. It also means like if I had a polynomial and a trig function, I can separate my integral into separate integrals. Completing the square, we see this mostly with our unit in chat or in section 8.4 with the trig sub, or even 8.3 with 8.2 with the inverse trig, or maybe that was chapter 5. Either way, completing the square. And certainly long division has come up. But I want to talk about what's new in this chapter. Starting with 8.2, integration by parts. Integration by parts is the formula integral of u dv is equal to uv minus v du, the integral of v du. And there's a reason why this formula does work. We go into that in the lesson, solving for this piece that we can't integrate as is. And there's ways to go about solving this, and the best way is to assign the appropriate u and the dv. Now that might not work in the first attempt. You may have to try again if it doesn't work. But certainly there's multiple options. You're going to have to be careful here. Some rules to guide you. Let u be the simpler derivative. Okay? If it's something that is getting more simple as you take the derivative, then you know that it's becoming a better integral to integrate. For example, if I have something like x cubed, when I take the derivative of that, I get 3x squared, and then 6x, and then 6, and then eventually 0, so that particular term goes away. I know that that's helping. It might take a long time, but it is helping. Something else you could do is let dv be the most complicated part, because you see dv is here, but it doesn't show up again, so we can actually get rid of it if we assign it away. If those don't work, choose again. Lie is a good foundation in choosing your u, meaning that you should pick your logarithmic function to be your u first, Any inverse trig comes second. Anything algebraic, third. Trig functions come fourth, and exponentials come last, because exponentials have just as difficult or easy derivatives and integrals. They're one and the same. So it really doesn't matter what you assign it to. It's not going to help or hurt your situation. The derivatives and integrals aren't the same. The integral coefficients are certainly different, but yeah, so either way. Consider the tabular method. That's a good way to organize your thoughts, especially if you have something like an algebraic piece that is moving down in exponents. You can kind of guide how big that is going to be. A quick overview of 8.3. We've got the rules for trig integrals. This is going to be your go-to when you take the test. If your sine exponent is odd and positive, save it. If your cosine is odd and positive, save one. If they're both positive and even, use one of these formulas to get rid of the exponent of a 2 and make it an odd exponent. You can see there. If it's secant and it's even positive, save 2 of the secants and convert it to tan. Save 2 of the secants for the derivative, because remember the tan is secant squared, and if there's an even number, then we know that we can convert the rest of them through identities. If tan is odd and positive, save a secant and a tan, and you're left with an even number of tans that you can change to secant. If tan is even positive and alone, then save a tan squared for the identity, and figure out from there. If secant is odd and positive and alone, use integration by parts. This reminds me of page 519 in the book, when it was secant cubed, and that seemed to show up quite a bit. So if you want a quick reference, there you go. And then if none of the above work, try converting everything to sines and cosines and seeing if one of these rules up here applies. Trig sub, we're looking for one of these 3 different radicals. If we have this radical, we use a cosine theta for the radical as a substitution. If you don't want to memorize that part, that's fine. Just remember that u is a sine theta. If you plug in a sine theta here, you're going to end up with a cosine theta anyway. The rules are there. Partial fractions, just a quick overview of what we just learned in the last lesson. If the integrand has an improper fraction and the numerator is greater than the denominator, then we're going to have to long divide first. Blank the denominator into the form. You're going to factor the denominator into its linear and irreducible quadratic factors. Linear factors will be of the form like a over px plus q, a2 over px plus q squared. I don't know, plus or comma. Until we get to a sub n, that's if we have px plus q to some power of n. I think we use m here, so we'll use an m. Irreducible quadratics will have linear coefficient or linear numerators. And finally, this is an n. So if I have my irreducible quadratic and it's raised to the 5th power, then I have to represent it for the 1st power, the 2nd power, the 3rd, the 4th, and the 5th. And each one of these numerators will be different, but they'll all be linear. At least they'll start with linear. All right, so let's actually do some questions here. A lot of these questions are going to look very much, oops, I lost my camera. They're going to look very similar to questions that will be on the assessment piece. So make sure that you understand this. If you have any questions, send me a message, and I will get back to you ASAP. All right, I see a radical and I see 6x minus x squared. This doesn't fall into any of the categories, but it looks most like sine because the x squared is written last. It's missing the constant, which makes me think of completing the square. All right, so let's take a second here. And if I factor out the x, if you remember x squared, the x squared term in completing the square has to be 1, so I have to take that negative out, which makes this a negative 6x. And I do completing the square on the middle term. Which means I need a 9 that I don't currently have. But by adding a 9, and be careful, I'm not actually adding 9, it was a negative 9. I need to balance it with a subtraction, or with an adding of 9, sorry. So this is actually a subtraction of 9 because of the negative that was outside the parentheses, and I balance it with a plus. So here's what it really looks like. It's the integral with 3 in the numerator of the square root in the denominator of this 9 minus the completed square of x minus 3 squared. Now if you're wondering where x minus 3 came so quickly, if you reduce your fraction in completing the square all the way, that number will be what's in the parentheses. Alright, so now I know it's of the inverse sine format. Not inverse sine, sorry. Trig sub. And let me make sure, because all of these lessons are kind of bleeding together. I want to make sure that I'm doing the correct thing first before I should have checked that before. Integration by parts is unnecessary. Okay, yep. Alright, so trig sub. A is 3, and u is x minus 3. du is dx. And actually, I don't need trig sub because this is, in its form, an inverse trig. So I apologize. This is referencing lesson 8.1 where we can use alternative methods. Or not alternative methods, review from the past of the different methods that we already know. So here's what I do know. 3 is the coefficient. This does not need to be balanced, and it is ready for inverse trig. You can use your book to remember the inverse trig or the inverse sine formula, but it's not. It's the only one that doesn't have 1 over a in the beginning. It is arc sine of u over a, and u is x minus 3. A is 3 plus c. Okay? That's referencing what I already should have known from the past. This one is a mix of an algebraic function and a linear, or not a linear, a logarithmic function. I do not have previous tools to help me solve this, so this is taken from 8.2. This is an integration by parts. And if you remember, integration by parts gives me this acronym that says, okay, your L, or your natural log, should be what you assign u to be from the beginning. And while we're there, the derivative of that is 1 over x dx. It has to be your u because we don't know the integral of the natural log of u. We just don't. So if this is your u, then dv is x to the 4th dx. To get to v, I have to integrate that. Okay? Integration by parts says that the integral of this function that we couldn't do, this integrable integrand, is equivalent to u times v minus the integral of v du. Which is nice because this new integral that's left is actually quite solvable. So I'm going to clean up what I see in front of me. I'm going to write my x to the 5th over 5 in front of my natural log, just because I want to make sure that, well, I like to write my algebraic terms in front. It just looks a little bit better. Minus the integral of, and I could bring the 1/5 out front, I suppose, okay, of x to the 4th. final answer is x to the 5th over 5 natural log of x minus 1/5 times x to the 5th over 5 plus c. You could clean this up and write 25. I guess I have the space for it. Okay. The next one is again a mix of now an algebraic and a trigonometric function, so it's still under the envelope or under the umbrella of 8.2. And of the two, the algebraic and the trig, the algebraic is going to be my u. Now here's the thing, if u is 5, then I know that I'm going to have to do this a few times. This is cyclic, so my v's, my dv's, and everything are going to kind of bounce back and forth all over the place. So I'm using my judgment and using the tabular method to solve this one. Which means I start with a positive x to the 5th cosine. I'm going to have 5x to the 4th as its derivative, then 20x cubed, 60x squared, 120x, 120, and I apologize for the spacing, and then finally 0. Each one of these lines is going to have a different or alternating sign in front of it, eventually a plus. And when I take my integrals, the integral of cosine, you can make your chart or whatever off to the side, but it's going to be sine. Then it's going to be negative cosine. Right? The integral of this would be negative cosine. The integral of that would be negative sine. And you're going to see a pattern real quick. The final answer is equivalent to a right arrow and then a down diagonal arrow. So x to the 5th sine x. I've got two negatives here, so plus 5x to the 4th cosine x. I've got one negative, minus 20x cubed sine x. One negative, minus 60x squared cosine x. One negative, plus 120x sine x. And this negative goes to that 120, which goes down here, so that's two negatives. So plus 120 cosine x. And then this last plus 0 is just your plus c. This has a lot of terms in it, so you'd see real quick if you did the UDV like we did above that you would only be getting yourself one step at a time from x to the 5th down to x to the 4th down to x to the 3rd, and it would be very tedious. So this is a much quicker way to solve that problem. Alright, now I've got sines and cosines, and I'm remembering in 8.3 trig integrals. The rule for sines and cosines, reference here, is if sine is odd and positive, which it is, save one of them and change the rest to cosine. If sine is odd and positive, save one of them and change the rest. So here's the one that's been saved. Change the rest to cosine. Using your trig identities. I'm going to distribute. Oops, too early for dx. And the reason that we went through this process is because cosine, regardless of the exponent, has a derivative of negative sine, which means that now I can treat these as u to the negative 1/2 and u to the 3/2 because I have du already set, which means that I get negative cosine to the 1/2 x over 1/2 and cosine to the 5/2 x over 5/2. To clean this up a little bit, it's negative cosine to the 1/2 x plus 2/5 cosine to the 5/2 x plus c. Still in the same category, I've got cosine to the 4th. If both exponents are positive and even, well, if we don't have a cosine, or if we don't have a sign, you know that it's 0, it's irrelevant. But in this case, we're in this category. Use either of the following. So we're going to use this formula to simplify what we have in front of us. So I have 1 plus cosine 2x over 2 times 1 plus cosine 2x over 2 dx. I'm going to bring both of these 2's out, which means I have a 1/4. And I'm going to FOIL to save some room. I'm going to FOIL what this says, giving me 1 plus 2 cosine 2x plus cosine squared 2x. 1 is integrable, 2 cosine 2x is integrable, cosine squared is not, so I have to do this one more time. And because each of these are integrable, it might not be a bad idea to break it up into 3 integrals, but I'll wait just a second here. Nah, I won't wait. They're all going to have 1/4 as the coefficient, or I can put 1/4 out front and box my integrals, but I'd rather just get through it all. And maybe you'll see why here in a second. Now be careful here. Because it's now squared on a 2x, this actually is going to become a 4x. Right, go back here. When we start with just a regular squared x, it becomes 2x. But if we square a 2x, then that doubles and it becomes a 4. Alright, here's why I wanted to break them up. I can bring this 2 out and look at that separately. The integral of 1 is going to be x. With the 1/4 that's there, it's 1/4 x. This 2 and that 1/4 cancel to a 1/2. And the integral of cosine balanced, well, let's see, I need a 2, and I have to balance it with another 1/2, so I guess I'm back up to 1/4 here. And it's going to become sine of 2x. And then my new coefficient over here is 1/8. The integral of 1 is going to be x. And the integral of this, imagine balancing it, a 4 and a 1/4 out front, so this is going to be 1/4 sine 4x. Now certainly I'm not going to have enough room to do this out, so I'm going to grab some paper here. Bear with me for a moment, I've got to find my paper. I'll just insert this with what I've been working on. So I end up with, all of them have 0 to pi over 6, so I'm just going to evaluate all of them with pi over 6 first. So 1/4 of pi over 6 plus 1/4 sine 2 times pi over 6 plus 1/8 of pi over 6. I'm distributing that 1/8 plus 1/32 of sine of 4 times pi over 6. And then I'm going through with the 0. All right, I have pi over 24 plus 1/4 sine of pi over 3 plus pi over 48 plus 1/32 sine of 2 pi over 3. It's 0 minus sine of 0 is 0 plus 0 plus 0. Alright, these I can make a common denominator out of. It's going to be double this. So I've got 3 pi over 48 plus 1/4 of, well, sine of pi over 3 is sine of 60 degrees. I'm not going to do my whole chart. 0, 30, 45, 60 would be right here. Pi is 0, 1, 2, 3. Not pi, sine is root 3 over 2. Sine of 2 pi over 3, well, 2 pi over 3 would be 120. 120 degrees is a positive number for sine in the second quadrant. Okay, I'm thinking of this. 120 degrees is over here. That's a positive sign because if you remember, it's ASTC. So I'm going to use my reference angle, which is 60 degrees, for that answer, which would also be root 3 over 2. We're getting there. See, I can make this 64 by making this 8. So in simplified exact terms, oh, that 3 and 48 can cancel. That's going to be a 1 and a 16. Plus 9 root 3 over 64. Now this is my exact answer. As a decimal, this ends up being, let's see here, pi divided by 16 plus 9 root 3 over 64, 0.4399. To make sure that I did that correctly, I'm going back into the beginning. So let's see, the very beginning was the integral from 0 to pi over 6 of cosine to the 4th, and remember I have to write cosine of x and close it, and then raise that to the 4th dx. Also, before I press enter, I want to make sure that I'm in radian mode, and it does end up being the same, so I feel good. Alright, moving on. Always, 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 always check your definite integrals. Okay, this one is another one from 8.3. I don't know if I marked that over here. Okay, the rule for sine or secants and tans is if tan is odd and positive, save a secant tan. Alright, tan is odd and positive, so I'm going to save not only the tan, but a combination of secant tan, because secant tan is the derivative of secant, which means this is just u cubed. Final answer becomes u to the 4th over 4th. If secant is even and there's nothing else around, save 2 of the secants and convert the rest to tan. This is equivalent to tan plus 1. And the reason we want to do that is because when I distribute, in distributing, I'm actually going to write it as 2 separate integrals. My secant x, my secant squared x dx is the du I need for tan cubed, which means it's going to be tan squared, which means it's going to be tan cubed over 3. And then if this is just the integral of secant squared, we know that to be tan. Alright, now we're getting out of that and into 8.4, trig sub. In trig sub, you are to assign your u and your a. U is x, which means my du is dx, and my a is 1. Now, if it's in the if it's an addition 1, then we know that it's going to fall into the tan secant category. This means that the square root, and I do have the square root, right, that says the denominator of 2 is the square root of this, is going to be equivalent to a secant, but the u itself is a tan, which means that it's derivative of secant squared. And then as I substitute everything out, my square root of that problem, I'm actually going to leave, I'll put the 3 on the outside and I'm going to change this to the square root. Maybe that'll be better to look at it. This becomes 1 secant cubed. And then my dx is going to be replaced with secant squared. 1 over secant is the same as cosine, and the integral of cosine is sine. Now our answer can't be in the form of sine because we didn't start with sine, so go back to a triangle, and we're going to convert out using this formula right here. Tan of this angle is x over 1, which means this portion right here is the square root of their squared combinations added together. Sine would be opposite over hypotenuse. So the final answer of x over x squared plus 1's square root plus c. Alright, now I could potentially try a u sub here, but I'd rather use a trig sub because the u came first. Then I know that that's going to fall into the 3 secant theta category, which means du is 3 secant theta tan theta theta. Alright, so I'm going to leave my bounds off for a second, and I'm going to replace x cubed with this formula, cubed. 27 secant cubed theta. If you need to write it out as 3 secant theta quantity cubed, that's fine. The square root portion becomes the brother to this, 3 tan theta. If you're not sure about that, you have the notes for it, but just imagine 3 secant theta being plugged in. It becomes 9 secant squared. The 9's come out, giving you a coefficient of 3 when you take the square root. And we're left with secant squared minus 1. Secant squared minus 1 is tan squared, and the square root of tan squared is tan. And then dx gets replaced with 3 secant theta tan theta d theta. Alright, so I have 81 times 3 is 243. Integral of secant to the 4th tan squared. Think about what you're supposed to do when they're both even and positive. Again, you're able to reference your notes for this. So if secant is even and positive, save 2 of the secants for the answer, or for the derivative, sorry. And convert everything else to tan. Make sure I did that multiplication right before I move forward. 27 times 9. Alright, so tan squared theta plus 1. I'm going to rearrange this and put tan squared here and secant squared after it. That's the derivative, or the du piece that I need. Can't get this done just right. Okay, let's try that. Alright, so I've got 243 integral of tan to the 4th theta plus tan squared theta times secant squared theta d theta. Remember, this was distributed into the parentheses. So without writing it out, I want you to imagine the integral of tan to the 4th with that appropriate du attached to it, and tan squared with that appropriate du attached to it, as if I distributed those and made separate integrals out of them, giving me 243 times tan to the 5th over 5 plus tan cubed over 3 plus c. Okay. The last one on this page looks like it's written to be ready for sine, sorry. Alright, if that's the case, then a is 5, u is 3x, which means it's now going to be 3 sine theta. du is 3 dx, which is 3 cosine theta d theta. Now, why is that special? Well, when you start to simplify this, you're going to need a 3 here with your dx, balanced with a 1/3. The balancing is very important. This radical piece becomes the 3 cosine theta from the substitution, and that dx, that 3 dx, becomes 3 cosine theta d theta. I can bring that 3 out, and I'm taking the integral of cosine squared theta d theta, which falls into the category of changing it to 1 plus cosine 2 theta over 2 d theta. This 2 can come out. I've got the integral of 1 plus cosine 2 theta d theta. I'm going to do some of this in my head, so I apologize. The integral of 1 d theta is going to be theta. The integral of cosine 2 theta needs to balance. I'd have to put a 2 here with a 1/2 out front, and then it becomes sine. I have to convert out using my triangle. Oh, and I didn't do that above, so actually I'm running out of room. Let me do that for both these two on a separate sheet. Let me backtrack. So this is question number 9. 243 over 5 tan to the 5th theta. I'll keep the 5 here. I don't like it there. Sorry for kind of jumping all over. My fault. So x over 3 is my secant, which makes this the square root of x squared minus 9. Tan would be that over 3 . me simplify this. That's going to now be x squared minus 9 to the 5 halves over 15. Sorry, not 15. Yikes. That's 3 to the 5th first. 3 to the 5th is 243. You see that happening, so I'm going to leave it as 243 for a second. And this becomes x squared minus 9 to the 3 halves over 27, and 3 is 81. And then I'm going to distribute that 243, which cancels with that denominator. And makes this denominator, 243 divided by 81 is 3. Final answer. So there's the fix of number 9. Okay, and then to finish number 10, so starting this triangle, according to the first statement, opposite over hypotenuse is going to be oh goodness, sorry. This should be 5 sine theta, right? Because that's my A value. This should be 5 cosine theta, which means this is now going to be, I needed the 3's, so the one, okay, we're going to do this problem over. So I apologize for that, that's crazy. But I will do this right away. So it's 3x and 5 over here, which makes this 25 minus 9x squared. Alright, so I've got the integral, and I put the 3 and the 1/3 in there already. The 3 and the 1/3, so I'm going to keep that. The integral symbol gets replaced with 5 cosine theta, and the dx, or 3dx, is the 5 cosine theta d theta. Okay. So then now this becomes 25 over 3 cosine squared theta d theta, or 25 over 3 integral of 1 plus cosine 2 theta over 2. 25 over 6 of theta plus 1/2 sine 2 theta. So none of that has changed. Plus c. I need to figure out this stretched out. There's an identity that says that sine 2 theta is equivalent to 2 sine theta cosine theta. Lucky for us, those 2's cancel. And my final answer, theta is going to be equivalent to the arc sine of 3x over 5 plus sine is 3x over 5, and cosine is the square root of 25 minus 9x squared over 5. I guess I could clean it up once more. And that's going to be 25. Oops, there's my camera. (25 over 6 arc sine 3x over 5 plus this 3. Oh, I'm not going to write it because I don't want to cancel it out if it's out in front of both of those terms, but that's going to be a 2 in the denominator, and those 2 5's are going to cancel with that. So this will just be x root 25 minus 9x squared over 2 plus c. I did a lot in my head, or I did a lot of it quickly, so double check that I did this correctly based on what you did in yours. Make sure every line makes sense. If you catch anything that doesn't make sense, by all means, please ask me to fix it. All right, we're going to wrap this up here pretty soon. Partial fractions. In order to do partial fractions, you need to know how to factor the denominator. Some clues, I would say, are factorable denominators. That's probably my biggest clue. Factorable denominators that would otherwise require completing the square if I wanted to do it in a different, use a different method. I know that this denominator is equivalent to x minus 3 and x minus 2. Those are both linear, which means my original formula is equivalent to a constant numerator over x minus 3 and a constant numerator over x minus 2. I also know that x plus 1 is equivalent to a times the other denominator and b times a's denominator. I could use let statements if I want, or I can multiply out. Rearrange. My x has a coefficient of a plus b, and my constant is equivalent to negative 2a minus 3b. That means a plus b has to be equal to 1. And that means negative 2a minus 3b has to also equal 1. These are the two numbers that I'm looking at. Multiply the top for, equation by 2. I get 2a plus 2b equals 2, and I still have negative 2a minus 3b equals 1. Using system of equations, solving a system of equations, I end up with negative b equaling 3. In other words, b is negative 3. And if a and b equal 1, a and b equal 1, and if I add 3 to both sides, I get 4. So if I want to take the integral of 4 over x minus 3 and the integral of negative 3 over x minus 2, I get positive 4 natural log of x minus 3 minus 3 natural log of x minus 2 plus c. If my denominator required balancing, I'd have to account for that, but I didn't have to in this particular question. All right, I think we only have one more question, and then we're going to wrap this up. This question here is a cubic denominator. If you're not sure what to do with cubics, you can always graph them, look for the roots, and then you know that those are going to be the at least the linear denominator. If you need to long divide, you can divide out. Let's say you had 2, you could divide out x minus 2. But I'm going to try using grouping first. X cubed and x squared have x squared in common, leaving x minus 1. I see x minus 1 showing up twice, so I'm going to pull that out front of both, leaving x squared, the coefficient here, and 1, the coefficient here. This is my denominator, okay? Which means that I have a root at 1, and then I didn't have any other roots. I could have long divided to figure this out, but I didn't need to. Alright, so I know that this is equivalent to a constant on top of x minus 1, and a linear function on top of x squared plus 1, that irreducible quadratic. Which means my original numerator, x squared plus 2x, is equivalent to a times the irreducible quadratic plus bx plus c times the first denominator, x minus 1. All right, I'm going to rearrange, or not rearrange this, but multiply it out. Minus bx plus cx minus c. I have a plus b as a coefficient in front of x squared. I have negative b plus c in front of x, and I have a minus c as my constant term. All right, so the coefficient in front of the x squared is equivalent to 1, which means a plus b is 1. Negative b plus c is equivalent to the coefficient in front of x. And a minus c is equivalent to the constant. There is no constant over here, so it's got to be 0. Okay, so here's what I know. A and c are the same thing, right? If I add c to both sides. So that means that a plus b is equal to 1. And if I put a in for c, a minus b is equal to 2. 2a is equal to 3, a is equal to 3 halves. That means that b, well, 3 halves plus what is 1? Well, that's 1 and a half, so that has to be negative 1 half. And then c and a are the same. Okay, b is negative 1 half, c is 3 halves, a is 3 halves. Okay, I know the first part. That part's easy. 3 halves natural log of x minus 1. But now I'm taking the integral of negative 1 half x plus 3 halves over x squared plus 1 dx. I don't like those fractions, so I'm going to take them out. And in order to do that, I'm going to go the other side here. Alright, I have 3 halves natural log of x minus 1. And I'm going to bring out a negative 1 half. Now, what's that going to look like? It's going to make my coefficient of the first term 1. And 3 halves, that was a positive 3 halves, is now going to be negative. What's 3 halves divided by negative 1 half, right? You can't divide by a fraction, so I'm multiplying by the reciprocal. And I'm going to end up with negative 3. All right. If that was a 2x, then this would be ready for u sub. It's not, but it can be. Meaning I can put a 2 here and a 1 half and balance that. That's ready to go. That's going to be just a u sub natural log. This one, however, is of the form of an arctan. Okay, so here's what I know. Once this u sub takes place, I end up with 1 half natural log of x squared plus 1. Absolute value is not necessary because that will never be negative. And this is an arctan where u is x and du and dx are synonymous, so it's just 1 over 1 arctan of u over 1. Okay, let me clean this up just a little bit. I've got 3 halves natural log of x minus 1 minus 1/4 natural log of x squared plus 1 minus 3 halves arctan of x plus c. There's certainly, like I said before, certainly an opportunity to double check my answers. I may have done something incorrectly. Check with me, make sure that it makes sense. If it doesn't make sense, question it, ask me. We're in this together. All right, if you have any questions other than that, please let me know. I will contact all of you individually at some point, and then we'll figure out our testing situation from there. Thank you.